Welcome. As is the name of the podcast, we start with thinking about a problem or opportunity, which is the first episode for any topic that we will discuss. Then, we build a product in the second episode, and on the third episode, we talk about how to scale a company using that product. We repeat the sequence of the nature of the episodes for all the topics that we will discuss in this podcast. So, yes, there will be 3 episodes per topic, and these 3 episodes will force us to think, to build, and to scale. Towards the end of all the 3 episodes, you will receive a full-fledged business plan and product development architectural plan to be used for your startup or your organization. Of course, you'll have questions and you will need a person to hold it all together. You can only learn so much from the internet, can't you? So please contact me in pretoria.b@outlook.com, and you can see my email in the top right section of the slide here. Please contact me if you want to discuss a remote or on-site tenure as a fractional CTO for your scale-up or your startup. You're also welcome to go through the introductory video of this podcast if you haven't already had. Today's episode will focus on the think part of the topic in hand. And the topic today is a transmission electron microscope. Now, why did I choose a transmission electron microscope or a TEM? In this episode, we'll just call it TEM, because I specialize in architecture for highly complex machineries. I treat the machine as a human body, and step by step, I decipher what is needed in various phases of the development of this complex product. Personally, the most complex machinery I have been a part of is the EXE 5000 by the semiconductor equipment developer named ASML in the Netherlands. If you are a founder of a startup or an executive within a small, medium enterprise, you would often spend sleepless nights wondering about how to defeat your competitors. You might also develop a revolutionary product, but it is only a matter of few years when competitors take over the slices of the market. If you are the market leader this year, like our nanoscience instruments, as you would see, if you are a market leader like them, your next set of worries is how to keep your position intact in the market if you cannot expand yourself further. We will talk more about staying big in the market and dominating new pieces of market in the third episode properly. Siemens introduced the first commercial TEM in 1939, but in 2025, in the list of top 9 companies, as you see here, you don't actually see Siemens listed. There are multiple reasons for this, but primarily if you are a larger organization that has multiple branches and multiple sub-corporations, you know when to kill a product line and not invest too much on a market because you know you're no longer a big player in that domain for whatever reason it is. And we will talk about the reasons later on or, as we go along. It is interesting that a company like Nanoscience Instruments, founded only recently in 2002, is further ahead than Geo Limited, look here, which is a Japanese high-tech equipment developer founded in 1949. Yes, right after the war cooled down. Multiple people will look at this situation in multiple ways. I have 2 major perspectives on this. First of all, never think of yourself as small and weak if you want to make a mark in a market that is already captured by gigantic corporations. One of the biggest advantages you have is focus. You can focus on a small fragment of the market and cater your company's roadmap as per that tiny area of expertise. But larger corporations, as the name suggests, are all over the place, literally. For them, it's all about dominating new markets and newer clients and expanding on real estate. You are cheaper and more focused for your customers when you're starting new. Customers in any industry love cheaper options and more attention from one's suppliers. Of course, you're also inexperienced and you will disappoint your customers in multiple directions multiple times. But so will the big corporations, and your customers know that. One of the nicest things I found in the website of Nanoscience Instruments is partnerships. You see here, I went to their website and I found various different partners. And these are just a snapshot of the different partners that they have. The website is a rolling one. The partners would just roll from left to right, and you could see more of those. So although founded in 2002, they partnered up with 10 different high-tech equipment providers to align their database and services with their partners. This helps the customer choose them along with other brands of equipment for setting up laboratories. Now, here is how this works. If you are a research lab or a hospital, you need multiple set of equipment, and the data from one to another should be transferable. At times, the samples analyzed at one equipment should be of same structure and size to be used in the other equipment. These are very small operational details, but those details are what makes an impact on why a customer will choose you over a brand that focuses only on expanding oneself. These things don't happen in one go. It takes decades to collect the right insights of user experiences and takes tough skin to swallow your pride and adapt according to the market. But that is leadership. And I'm going to talk more about corporate leadership in this episode today later on. But now here's the thing. Another piece of information that I want to add here is from a public eyes perspective, these companies are ranked as per the amount of market they hold for the TEM systems. You see in the share of the market that they hold on the right side here in the screen. But one thing to note is that this is not the entire story for their success. For example, Thermo Fisher Scientific has over 2.5 million commercial products in their portfolio. Geo Limited has semiconductor lithography equipment as one of their products. The Max Planck Institute for Marine Microbiology is more of a distributor of research equipment than a developer and supplier. They are at best researchers. I'm talking about Max Planck. They are at best researchers who would also add some value in setting up your laboratory. Just like Nanoscience Instruments took over Siemens, the pioneer of commercial transmission electron microscope, there are some potential players in the market as well who display optomechanical and optomechatronics competence and therefore can hold a good share of the market of TEMS one day in a few decades. So what I meant to say here is that even though it looks like Nanoscience Instruments is having 26% of the market of TEM, that doesn't mean that in general Nanoscience Instruments is doing better than Geol or doing better than Hitachi or doing better than Thermo Fisher or any other brand. Thermo Fisher is not even included in this list, but they do develop TEM systems, and they also develop, like I mentioned, 2.5 million other commercial laboratory products. So it's all about the focus. So if you really want to dominate one market, it is very much nice to have one type of product and focus on that market itself so that you can really become a specialized name in that market, and your customers will think twice before going to your competitor who could be busy doing other things as well, who could be busy dominating other markets as well. But of course, we're going to talk more about that during the third episode here. Before I go further onto how to develop a TEM system, I want to bring to perspective the sensitivity of these equipment. Now look at the picture to the bottom right here. The transmission electron microscopes, or TEMs, are pretty incredible tools. They're used to peek into the microscopic world at magnifications ranging from hundreds to millions of times. Now imagine being able to see entire cells that are only tens of micrometers wide, or even the tiny arrangement of atoms just a few angstroms across. And that's around 0.1 nanometers. TEMs are super versatile, and they find their way into analyzing all sorts of materials, from semiconductors and ceramics to the biological samples like cells and bacteria. By tweaking the lens system, you can observe electron diffraction patterns, and with an added spectrometer, you can dive into elemental and state analysis. Once again, we will talk about that gradually. You do not need to worry about remembering every single piece of technical terminology I present here. And unlike scanning transmission electron microscopes, or STEMs, TEMs actually let you capture all of the data in one go, which is very handy for watching how the structure of an object changes over time. Here is the general working principle of the TEM. TEM works, this is a diagram of a TEM that is generally used in university levels, or sometimes even high school level education. Look over there, we shoot a beam of accelerated electrons at a sample, which is right here. And the sample could be super thin, which could be no more than around 100 nanometers thin, to give you an idea. And that's about 1,000 times thinner than human hair. So we shoot a beam of accelerated electrons at an extremely thin piece of sample, and it would pass right through it, because these electrons travel and they scatter, and throughout, with the difference in the structure of the sample, it will scatter differently. This scattering is crucial because it creates contrasts in the image that we eventually see. And we see the image here in the detector where they're displaying. Don't worry about remembering all of that, because we're going to go much into detail gradually in this episode and in the coming episode. If you're at home listening, just listen, absorb. Do not worry about remembering each and everything. Once again, we shoot a beam of accelerated electrons at a sample that is not more than 100 nanometers thin, and 100 nanometers thin would be around 1,000 times thinner than human hair. And then we let those electrons pass right through these materials, and these electrons travel and they scatter differently depending on the internal structure of the sample used. Now, this scattering creates contrasts in the image that we eventually see, just like how shadows and light work in a photograph, but of course in a much smaller scale. And this way we see the inner details of the sample down to atomic level precision. But for now, if you look into your picture, this is how the transmission electron microscope works. An electron gun, a focusing length, your sample right here, your objective, and then this is where your detection system is. And this is where you can see. Don't worry about it. We're going to talk more about it in detail gradually. Before I go further, this episode is all about showing the thought process behind having a business that would sell or that would develop a transmission electron microscope. Just remember that. This episode is all about the business level discussions, the business level thought processes that go with it. So a startup will approach the business development and product conceptualization phase very differently. Most of the time, the conceptualization and development is outsourced to an engineering firm that has the expertise and time to go into the details of mechanical, electronics, optics, and radiation. In an SME, the board wants to have more control over the day-to-day operations of the company, where the various departments need to have close communication with one another. A lot of times, the intricate technical details are what keeps the company floating ahead of its competitors. So it's important to keep those employees within the confines of your organization. In many other cases, the services that the company provides after selling the product is what keeps them ahead of their competitors. So those experienced and trained professionals become an intricate part of the organization's goals, philosophy, and profit generation process. For this hypothetical product, we will call it TEM Gen Z. TEM is transmission electron microscope, and Gen Z just because we're talking about the future. So TEM Gen Z, first thing to consider making this product is to fix the business goals of releasing this product. One thing is for sure, most established companies do not simply make a product. They find a buyer first, spend a lot of time in convincing and winning the customer over. The technical team works out a concept. And if the company is lucky enough to be at a stage where they have a unique functional prototype, they generally use that as a mating call to their customers. This is no different than a startup where the founders spend a lot of time preparing the business plan and showing the promise of a product through a functional prototype as they seek investors and customers simultaneously sometimes. Nobody said it would be easy. Being an entrepreneur is tougher than being anything else on earth. It takes a special mindset and special personality to stand on nothing while you promise everything. And I say that with a lot of positive connotation for entrepreneurs. I've been one myself, and I have a lot of respect for those who have built their own companies. Kudos. During this period of dancing with the customer, the investor, or investors or shareholders, there will be one and only one major thing that will sell them the product. I'm sure you know about it. I'm sure you're thinking about it already. Return on investment. It is therefore important to show how the cost of development would be cheaper than today's solutions. It is important to show what the market wants and to show that there is even a market for this product. The investors would also want to know how would this new startup or scale up approach the market, from which segment, which location, what is the exit plan if one particular market segment rejects this new product. They would also want to know if there would be any problems during the operational side in terms of safety and reliability of the product for the end users. And now finally, one thing, and only one thing will make them open their wallets: the duration. The shorter the time to production and then to the market, the faster is the probability of receiving return on their investments. That duration will be the final topic to handshake upon. One of the things that people often forget is that the inside of a product means nothing to the customer, unless they want to, of course, reverse engineer and build it themselves, which they won't because they're too busy trying to concentrate on their primary businesses, of course, which constitutes using the equipment and making value out of that usage. But at this stage, you can already distinguish yourself as a professional and serious applicant for their business by using Six Sigma tools like Kano analysis, Buick matrix, and affinity diagrams. These tools help in clarifying the project goals or the company goals, the scope of your company, the technical scope, the market scope, etc., and then your key stakeholders, of course. Details about these tools that I mentioned, your Kano analysis, Buick matrix, affinity diagrams, I'll make another episode. I'll make a series of episodes that are called Six Sigma statistical tools, and you would find the details there on how to use these statistical tools in your business goal development phase. Whether you're a startup, you're a scale up, or an established company, you could use these tools anywhere once you actually know what they are. Let's go back to system. This slide that I'm showing right now, I don't know if the listeners will not be able to see your slide, but as a person, if you're viewing it from somewhere, I must say this is my favorite thing to do. I loved breaking down the functional aspects of the TEM machine. Again, this is not something that I did as a part of my job or anything. This is just purely out of interest. I wanted to think about how to build a TEM system, how to build a transmission electron microscope. And the first thing to do is, of course, look at the various different process that goes on. Now, at least the CTO of the organization, of a startup or a scale up or an established organization, if not all board members, need to know the system that they are developing and selling. So if you're a CTO of an organization and you are considering building an optomechanical equipment or any capital equipment, I think this is a very important section of the episode for you. Most of the details should be on the shoulders of technical and people leadership, of course. But as a CTO, you really need to know what's happening inside of your machine. This flow diagram right here, it shows how the functional process of a transmission electron microscope is broken down. It shows various steps from sample preparation to image analysis. Now here is an in-depth explanation of the main steps. You start preparing your sample, which could be less than 100 nanometer thick. And this specimen is prepared using techniques like ion milling, ultramicrotomy, cryosectioning, etc. You mount this sample into something called a TEM grid. It is a component within the TEM. Don't worry, we will talk about the components later on in the coming episode. But the prepared sample is mounted on a specialized grid to ensure stability and transparency of the electron beam. The sample holder maintains its position within the TEM. The sample holder also contains a vacuum system, and the sample holder is inserted into the microscope's vacuum chamber to prevent electron scattering by the air molecules. High vacuum levels of around 10 to the power minus 6 torr are maintained for precise imaging. It could be even lower than 10 to the power minus 6. So let's see. So here is where the vacuum is taking place. And the reason for having vacuum, as I mentioned, is to prevent the electron scattering. We need the electron beams to be focused on the sample and not be scattered everywhere. There are various different design methods also how you can achieve that, but that's again in the second episode. Electron beam generation. Now the electron beam is generated by an electron gun. It's called field emission gun. And we will talk about it and we'll look at the design, etc. in the coming episode. The electron source generates a highly focused and coherent electron beam. The acceleration voltages are around 200 to 300 kilovolts, and they define the energy of the electrons, of course. You have a beam alignment system using condenser lenses. The condenser lenses focus and shape the beam. They control the beam's coherence and convergence before it interacts with the sample. What is coherence and convergence of the beam? It's simply, I could go a lot into the details of it, but it's simply the ability of the beam to be focused in one direction and not lose energy, not be scattered everywhere. That's basically all there is to it when I talk about coherence and convergence. When the beam reaches this specimen, we have interaction, of course. This interaction could be elastic and inelastic scattering. Elastic scattering would be where the electrons interact without losing energy. and they are useful for structural details, while the inelastic scattering would be when the electrons lose energy, and they are useful for compositional analysis. What does it even mean? Magnesium would react differently than oxygen. Hydrogen will react differently as nitrogen. So based on various different methods, various different scattering images, you could figure out the elemental composition of the samples. Of course, you need to be. There are certain specialized technicians who should be looking at the data for that. Let's go back again to our TEM. The sample is mounted on a motorized piezo-driven stage that allows movement in X, Y, and Z directions, along with tilt and rotation for optimal imaging angles. And these angles also matter, and they play a role in the elastic and inelastic scattering, because light will react in all different light will behave differently with when it hits a sample in a particular angle. There are ray optics courses on that, which will be around 5 to 10 hours if I want to go into the details on how light will behave. But in general, coming back to our TEM, in the objective lens, the primary image of the sample is formed, and then the aberration corrections are applied to improve the image quality. In the intermediate and projection lenses, magnify the primary image further, and then they project onto the imaging plane for field of view adjustments. The lens, I understand that the lens system is quite difficult to process and to understand. I could make 3 or 4 different episodes only to describe about the lenses. So for now, I would ask you to bear with me and not worry too much about understanding each and everything. There is a lot of technical jargon here. There is a lot of business jargon here, but I would just say, please listen out the entire episode. And towards the end, I'm sure you will gain a good insight on how to build a business that would be able to make profitable transmission electron microscope. Because if you are a CTO or a CEO or a marketing executive, you do not necessarily need to know every single detail of lenses and image formation and scattering and selecting the right material, etc. All you need to know is what kind of people or what kind of companies you need to partner up with. That's mostly what you need to know. If you have any feedback on my explanation, and if you need more clarity on certain topics, and if you really, really want to understand certain topics, please do write to me in my email address that I already provided. I would be very happy to help you understand the deeper aspects of a transmission electron microscope, or any other topic for that matter. Let's come back once again to our flowchart. Let's talk about the detection and the signal processing area. So we talked about sample preparation. We talked about how the sample is loaded onto a vacuum chamber, and when it's loaded into the vacuum chamber, why is it loaded? Because electron gun is about to hit the sample. So the sample is mounted onto a vacuum chamber, and the electron gun transmits electrons into the sample, and after that, the image that is formed using elastic scattering or inelastic scattering is further processed using a lens system. You have the objective lens, and you have the intermediate and projector lenses, and then finally they arrive here to the detection and signal processing system here. What is this? It's nothing but a CCD camera. It's a highly sensitive camera that detects the electrons transmitted through the sample. The camera digitizes the signal for real-time viewing and data recording. The digital processing enhances the image brightness, contrast, and resolution to highlight the fine details. Image reconstruction. Now that's a study on its own. Advanced image reconstruction algorithms correct distortions and noise, and produce a high quality image for interpretation. And these interpretations, as I mentioned earlier, could be structural, where you see the structure inside a sample, or it could be compositional. You could see what the sample is actually made of. Is it a metallic one? Is it a biological one? What is the sample exactly? Measurements such as distances, angles, and atomic structures are primarily extracted when you look at the quantitative analysis part of it. Now, most of the TEMs around in the market, they provide real-time viewing and final interpretation. The processed image that is displaced on a real-time screen, they allow interactive monitoring. The final images are saved for further analysis and comparison. In general, if we look at the overall sequence of the transmission electron microscope, I can run it once again for you. Step 1 is to prepare the specimen, which is the sample. The sample is prepared to a thickness of less than 100 nanometers. It ensures that electrons can pass through it. Methods like ion milling, cryosectioning, or ultramicrotomy are used. Ultra-thin samples are critical for TEM imaging because electrons need to interact with the material without scattering excessively. Step 2 would be mounting the specimen right here. Would be special. The prepared sample is mounted on a special TEM grid. This grid holds the sample securely in place. The sample grid provides a stable platform for the specimen, ensuring that it remains aligned and stationary during imaging. Loading the sample into the holder and then the vacuum transfer. The grid is inserted into a sample holder and then that is loaded into the TEM vacuum chamber. The vacuum levels could be 10 to the power minus 6 torr. And it's that high level of vacuum because we want to prevent air molecules from interacting and interfering with the electron beam. A vacuum is essential also to maintain the electron beam's energy, precision, and even a few air molecules could scatter the electrons. Electron beam, step 4 is electron beam generation. The field emission gun generates a highly coherent electron beam at adjustable accelerating voltages, 200 to 300 kilovolt. The beam is aligned and focused using condenser lenses to control its size and intensity. Focused high-energy electron beam is necessary to produce detailed images at atomic resolutions. Step 5 would be sample interaction and stage adjustments. The electron beam interacts with the sample, and these interactions could be elastic or inelastic scattering, as I discussed before. Electrons scatter without losing energy. They provide structural details, and this is called the elastic scattering. When the electrons lose energy, they offer a compositional information. The sample stage, which is a piezo-driven motorized system, allows precise movements in the X, Y, and Z directions and even tilt adjustments for optimal imaging angles. Precise control of the sample's position and orientation ensures that the area of interest is properly analyzed. Step number 6 would be the formation of the image itself. The objective lens forms the initial image of the sample based on transmitted electrons. Corrections are applied, and because things like spherical aberration, etc., they need to be corrected. What are spherical aberrations? Don't worry about it. These are simply errors when the light is interacting with the sample and the data is translated into a detector system. These are simple errors and they need to be corrected. As simple as that. They are corrected to enhance image sharpness and reduce distortions. The objective lens is critical for resolving fine details in the sample. What happens during image magnification, which is step 7? Intermediate and projector lenses further magnify the primary image and project it onto the imaging plane. Field of view and resolution can be adjusted at this stage. These lenses allow flexibility in magnification, and they enable imaging of both wide areas and atomic scale details. Step 8 is detection with the CCD camera. Right here in this image, the CCD camera translates electron interactions into a visible and recordable image for an analysis. Step 9 is the signal processing. The digital image undergoes signal processing to enhance brightness, contrast, and resolution. This ensures that the finest details are clearly visible for interpretation. Step 10 is image reconstruction and enhancement. Step 11 is, of course, your real-time viewing and the final interpretation. So these are generally your basic steps. Prepare the sample, mount and load, generate and align the beam, interact with the sample, form the image, magnify and project, capture with CCD, process and enhance, display and interpret. The interpretation is where your skill and your knowledge from your high school science level or your university degree, that's what come into play when you're looking and interpreting and you're interacting with the TEM image. Look at this, how beautiful. The viewers who are watching this from your screen and not really listening to it as a podcast from your car or your train journey, you would notice a beautiful image of a stage of a piezoelectric 6-axis stage of our TEM Gen Z. This is very, very hypothetical, AI developed image. This is not a real image that I have designed, because of course everything that I have designed or I have taken part in at my work, I am not able to display it. And this is just a knowledge-based discussion from my side. Look at this. This image shows a 6-axis stage, a stage that enables 6 degrees of freedom, which include 3 translational axes, X, Y, Z, and 3 rotational axes, pitch, roll, and yaw. Let's analyze the image systematically. The linear axis, which is X, Y, and Z. Axis motion is the visible horizontal actuators allow movement of the stage. It's laterally from left to right. Precision screws or piezoelectric actuators control the displacement along this axis. Orthogonal to the X, the Y-axis orthogonal, which is at 90 degrees here. The Y-axis motion provides front to back positioning. Linear and the linear guides combined with flexure hinges ensure smooth, backlash-free motion. Z-axis motion, which is a vertical movement up and down, is controlled by actuators attached to the stage base and support rods. The Z-axis actuation is used to adjust the sample height for focusing and alignment. A rotational axis, an axis which is your pitch, roll, and yaw, it could be along the X-axis, along the Y-axis, and along the Z-axis. Pitch is the rotation around the X-axis. Pitch is achieved by tilting the platform forward or backward around the X-axis. Flexure hinges and precise actuators allow this movement while maintaining alignment. Roll, which is your rotation around the Y-axis, involves tilting the platform side to side around the Y-axis. Rotatory actuators or simple mechanisms enable this rotation with nanometer scale control. Yaw, which is the rotation around Z-axis, refers to rotating the stage horizontally around the Z-axis, azimuthal rotation, as it's also called. The base or central pivot appears to support this rotational movement, and it's likely derived by a rotary actuator. How does it all work together? The flexure hinges, the piezoelectric actuators, the sensors, they control these movements. The flexure hinges connect the movable parts of the stage and allow precise rotational and translational adjustments without backlash. The flexure designs are critical for vacuum environments like TEMs, since they eliminate mechanical wear and reduce contamination risks. Actuators control motion in all directions, and they should be attached to various areas of the stage for controlling linear and rotational movements. Sensors could be capacitive, and they provide real-time position monitoring, and they enable closed-loop control, which is essential for maintaining accuracy in all 6 degrees of freedom. This combination allows the operator to align and position the sample with high precision for imaging and analysis in the TEM. Remember, I was talking about why stage adjustments are very important to minimize or to make sure that the electron beam properly interacts with the sample. So using 6-axis stages like these, you could achieve that. Let's go back to our main page. There you go. Why did I show you this incredible mechanical design? Why did I do that? It's because even though we are talking about board level discussions, one of the things that could potentially mesmerize a customer's attention, but not necessarily retain the attention, would be showing something disruptive and innovative. So most of the times, 6-axis stages are not something that is being done in today's market's TEMs. But if you show them an image like that, if you show them this and you explain them about your flexure hinges, the capacitive sensors in various areas, your actuators, I'm sure this is one of those things that investors would appreciate to a good extent. But of course, a lot of it is with how much does it take to develop it properly, and will they have a good return on investments? That's the final straw that would help you receive your millions or your billions from them. But anyway, we have a good thing on paper. TEM Gen Z, the product, we talked about the vision, that is develop a business around transmission electron microscope. We looked at the market. We looked at the various different business goals. We talked about cost, the profit margin, the market segment, attraction, safety, reliability, all of that. Then we looked at how the functional breakdown of the system is. And then we looked at one of the example, I would say, disruptive technology that would help you gain attention of the investors. So let's say you have received some millions from your investors or your shareholders. You have now a good thing on paper, and the leadership below you that you have hired, they understand what to produce, what to design, etc., etc. But how do you manage such a Herculean task? Because there is also a lot of money in making and selling bread, but you aren't a bread maker. You are in the business of innovation. Your interests are unconventional and futuristic. So what do? You have to bring in organization and structure in your company, whether you're a scale up, startup, or an SME, which is small, medium enterprise. It doesn't matter. Organization and structure is the only thing that will keep you ahead of your competitors and keep rolling the money-making machine for you. With that in mind, we go to the next step. So next slide. So until now, we have discussed the business goals, the functional breakdown, the working principle of the TEM, the functional breakdown of the TEM on what goes on within it. And then we also talked about one of the mechanical components, which could be potentially your piece of attraction for disrupting the existing market, because you do need innovation. So if you want to make a camera is nothing new, right? If you want to build a camera and you want to sell it, you want to start a new business out of it, I mean, nobody is going to invest in a camera because Nikon, Canon, they have already taken the market. Forget that. Your iPhone, your Samsung, they have taken over the market of cameras. But then what additional thing can you add? Perhaps you want an IR camera. They also exist, but perhaps you want a camera that can connect to the future, whatever it is. So it's always a small technical detail that is of interest to your investors that will help them understand that, yeah, you have given it a good thought. It's not just about wearing a suit and going and asking for money. You also have depth in you. That's the reason I showed you a concept of a 6-axis stage like this, to show that, yes, we know the market of TEM. It's nothing new, but we are adding something new to it, and that is the ability to rotate and view the sample in 6 different degrees of rotation. Well, it becomes 12, because you have x, y, z, minus x, minus y, minus z, and then rx, ry, rz, and then minus rx, minus ry, minus z. So there are various different ways that you could use your 6-axis stage, and that would help in the image formation. But that is, of course, not enough. As I mentioned, we need good organization. What do you do for organizing your scale up and startup? Because remember, your shareholders, your stakeholders, your investors would also want to know, are you doing enough to hire the right people and keep them in check, and make sure that they have the people that you hire, or the companies that you partner up with, have you thought of it enough that they are able to do their job perfectly? So you, in the board of directors, if you are here, if you're one of these members, it also falls on you to make sure that the organization of your company is, if not perfect, at least somewhat functional. With that in mind, let's go to the next step, V model. Oh, I love this so much. I have worked with the V model in a company called ASML. This company develops semiconductor equipment. They develop lithography equipment, and most recently they have released EXE5000 and EXE5200 to the market, which is world's most complicated machine. Therefore, you could see, and I've worked in that machine actually, and therefore you could see that my mind is so much towards complexity and managing complexity and looking at things that are absolutely impossible, but then you just somehow bring them together. I love complexity, whether it is mechanical design complexity or data analysis complexity or even organizational complexity. But anyway, in the introductory video, I described what is the V model and what is Design for Six Sigma methodology. I also mentioned how to incorporate them both and why. The DIDOV and DMIC methodologies are structured approaches used in Six Sigma for process and product improvement. Each phase within these methodologies utilize specific statistical tools to analyze, improve, and control processes. I will explain both methodologies of Six Sigma, DIDOV and DMIC, and the statistical tools typically employed in each step. But don't worry, I also have another episode where I would describe all the statistical tools. I would make each episode for every statistical tool. So don't worry about that. For now, just hear me out. DIDOV means define, identify, design, optimize, and verify. In the define phase, you look at the project goals, your business goals, your customer needs, and your project scope. In the identify phase, you identify the critical requirements and specifications of the customer. In the design phase, you design the product or the process. In optimize phase, you, of course, optimize it, and you look at it from various different areas, various different aspects, and you optimize the product. And in the validation phase, you confirm that the product or process meets customer and regulatory standards. DMIC is nothing but define, measure, analyze, improve, and control. DMIC is to define the problem, measuring the problem, quantify the problem, analyze, identify the root cause and analyze it further, look at the defects or inefficiencies. improve the process or improve the machine or improve the product. And then, of course, add control measures to ensure that the improvements are sustained over time. Both Didov and DMIC provide a structured approach to quality and process improvement, and they use statistical tools to gather insights, guide decisions, and ensure outcomes. But it's not about statistics and design for Six Sigma in this episode. In this episode, I wanted to talk about how to build a transmission electron microscope, and how to organize your scale up or your startup for ensuring the generation of a product which is that complex. Once again, please check the introductory video on what is Six Sigma and what is a V model, please. So since the V model is a product generation process for new products, for embedding the Six Sigma methodology into the V model, the Didov methodology should be used. To integrate the Didov, which is define, identify, design, optimize, and validate, the V of a transmission electron microscope, we can map each phase of Didov to corresponding stages of the V model. This approach not only ensures systematic and development from conceptualization to validation, but also embeds Six Sigma's focus on quality and efficiency at every step. Now, trust me, you sitting in the board, look here. If you're one of these people and you are talking to your shareholders, your stakeholders, after they have provided you with the money, listen, by this time, you have your business goals straight. Your goal is to make money, as simple as that. I mean, as an engineer, I had all these philosophical things in me that, yeah, I want to break through. I want to create new products. I do. But if I am in the business of making a product, if I have a company, my goal has to be how to make money. It cannot, okay, to an extent, it is serving the community and being a part of something big, fine. All of that is fine. But when you're one of these people, trust me, when you're one of these people trying to talk to your shareholders, trying to talk about TEM Gen Z, the only thing that's of interest to your shareholders and your investors are how to receive a return on investments. So we talked about the business goals. We talked about your system. You have a complex machine, and then you know how the machine is being built, the functions of the machine. As you see here, the functions of the machine. And then we also talk about what is unique in your machine, right? So next step would be about showing your investors and your shareholders that using the money that we have received so far from them, we will put it to good use. How do you do that? You have to show them that you have organization within your company. And what I am trying to show you here are two proven methods designed for Six Sigma. They are used by the automotive industry primarily and the aerospace industry. And then the V model, which is used by semiconductor giants like ASML and Samsung and Intel. All right. I want to bring both the worlds of design for Six Sigma into V model. Why? V model ensures communication between various different departments properly, and design for Six Sigma uses statistical approach and data-driven decisions at every step. Remember that. That's more or less what this is all about. Let's go to the V model again. All right. Starting here in the V model is our system level concept. You have to understand the market demands, the end user insights, the high level goals on overlay, focus, and throughput of your TEM Gen Z system. You could possibly use tools like Kano analysis, Pug matrix, TRIZ, etc. These are Six Sigma tools, statistical tools. And like I mentioned, you will find a series of episodes on that as well. When you use that, you are actually talking to your shareholders and your stakeholders using a set of data. You're not simply talking and making promises. You are really using numbers and actual statistics. Statistics could very well be bent, But if you have good transparency on your data, on where your sources are, etc., your shareholders will be extremely pleased with you, and you will create credence to your presentations. And trust me, you want to be known as a leader who creates credence for themselves and does not just speak out of the whim. All right, system level concept. After the system level concept comes the system level requirements. Here is where you have to develop specifications and tolerances. You can use tools like the PERT chart. You can actually use FEA tools like COMSOL, NX simulations, CCM, etc., to make block model simulations and receive high-level specifications that can be translated, transported to modules and components. I'm sure and you should data analysis tools like Minitab and MATLAB in it. Now, here's the thing. I know a lot of the things are not clear for you. I understand a lot is not easy for you to grab at once if you're very new to systems or complex machineries, or even to the world of architecture, to the world of startup, to the world of, I don't know, just development. So I understand it could be daunting and it could be new. But like I said in my very first episode, this is not a high school level science explanatory series of videos. I'm talking about real life business challenges. I have worked in complex, high value capital equipment since the last 12 and a half years now in various different industries. So I'm sure my audience is out there, and I'm sure I'll reach out to the right audience in due time. But if you're new to my podcast and you're new to the world of development, please bear with me, and let's solve this mystery together. Let's decipher this mystery piece by piece. So from system level concept, we go to system level requirements. Then we go towards module and component level ideation and execution phase. Look here. System is where you have mechanical, electronics, software, fluids, optics, everything together. And then when you have module and component level, you can separate between various different disciplines of teams. So things become a little bit, I would say, easier. So there are people, so if you're in the board of members, if you're here, it is your job to place the right people in all of these. In module and component level, you also develop specifications, but tighter specifications again, and you develop tolerances, and you use Six Sigma tools like design of experiments and design FMEA. Every company is dependent on suppliers, tooling for testing and logistics. Here in this area, you can also use Six Sigma tools like Gauge R&R is to look at your measurement systems for looking at the validity and the reliability of all of your tools, testing tools, testing equipment. You have your process FMEA, SPC, statistical process control, and control charts. Once again, there are various different sources in the internet to look at them if you really want to understand them. Once you have information on the execution of module and components, you go to the verification of module and components after they are finished, after the supplier, the logistics, and the toolings have done their job. You have to verify them. So you verify them in two levels, which is one at module level. You go through Gauge R&R, PFMEA, SPC control charts again. You look at tests at various influential conditions, and then you compare them to the existing requirements. Where do the requirements come from? Here, here, and here. So then we go to system integration and verification. So here are modules. So let's say you have 20 modules. you build them, you test them separately, and then you integrate them here at system integration level, system integration and verification stage. At this system integration and verification stage, you will look at tests at upper and lower limits of operations. You test at various influential conditions, compare them to the existing requirements. Where do you get the existing requirements? From here. And from here, sometimes from here. People who are listening to this podcast, apologies for the unclarity. I'll go again. So first we have system level concept, then we have system level requirements, then we have module and component level ideation and execution, and then of course we take help from suppliers, we bring in testing tools, we bring in logistics, etc. We build the components one by one. We therefore verify the components and compare them to the required requirements. The requirements of the verification at component and module level will be found at the requirements set at module and component level ideation phase. If we have 20 different modules, we bring them all together, and that's called system integration. We verify them at various conditions, and we compare them to the existing requirements, and the requirements are found at the system level requirements that we discussed earlier. Then, of course, we at one point we decide, fine, the machine or the system is ready. The processes here, right here, are the processes at supplier's side or at the production site in your own company. The processes for making, let's say, 100 different machines or 100 units or 1,000 units per year or more, they are ready. So therefore we go to the customer, therefore we deliver the machine to the customer. But remember, you do need a plan. You do need this organization within your scale up or your startup if you are working with high value capital equipment. Without this organization, no investor is going to want to continue with their relationship with you. So then, yeah, you go to customer and you receive your insights from the market. You see how things are going. There will be certain escalations. There will be certain problems in the first few years of the product being placed in the customer, and you learn from those escalations. You learned from those problems. You look at the market trends on cost, quality, the need for innovation, etc. You do your research with the customer. You can use several Six Sigma tools like DOE and SPC for that. And then, of course, you provide those insights to build a system level concept, again, for a new system. That is how it is. Let's go back once again. My goodness, so much of talk, so much of technical knowledge, as well as knowledge of organization, as well as discussions with the suppliers, the stakeholders. Oh my goodness, so many people, so many parameters. I know it sounds daunting, but at the heart of it all is knowledge, 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 and knowledge. That's why I love this world of capital equipment so much. This world of high-tech equipment cannot be complete without knowledge and information from the past on the lessons learned. Neither experience, nor knowledge, nor passion alone will drive the company. What drives the company is actually good, empathetic leadership at every level. Look here. I definitely believe that leaders are born. They're neither created in the boardroom nor in the parents' living room, certainly not in a classroom. Commanding people does not work in technical environments. Your engineers will leave if you start commanding and cannot prove that you are smarter than them. You cannot be smarter than them, because if you are smarter and more knowledgeable, you need to be working in making the design choices and other calculations. You, as a technical or people leader, whatever you call yourself, you could be a CTO or a CEO, you have to learn how to balance knowledge with emotional depth. You need to know enough about what needs to be done and yet have enough of emotional maturity to foster an environment of pride and support amongst your team and or department. Throughout the last decade, I have been in technical environments in various countries. I have met many emotionally matured and distinct individuals who made it to the top because of their ability to handle challenges. They could detach themselves from people's actions, words, and continue with patience. I therefore truly love the field of engineering so much because if you're smart and proficient in one direction, that's good for you. The company will want to keep you. But if you can juggle multiple heavy balls in the air, you are rewarded with appreciation from your colleagues. Soon, that appreciation turns into new opportunities. You, of course, have to look for those opportunities. Leadership skills, right here on the left side, should be balanced with innovation, reliability, and quality of your deliverables. The ability to adapt and empathize, mediate and protect, guide and illustrate, manage your expectations of stakeholders, and help without spotlight. Oh my goodness. It is so easy to write all of these and so difficult to actually work in a corporate environment. I have been in the corporate world since what 2011 now. It's been a challenge, I would say, to always remain positive and to always balance my leadership with the ability to innovate and to deliver reliable and good quality products. So in terms of innovation, you need the architecture of course, highly complex systems, but you also need to adapt and empathize with all of your stakeholders that are there. The V model I showed you is not possible without good communication. Balancing innovation with reliability. I don't know a single person who is able to innovate, who is able to bring in new products while making sure that it's actually reliable. And when I say reliability, I don't mean as in philosophically reliable, but I mean reliable as in through the fundamentals of reliability engineering, where you make sure that a minimum of 65% of your products will last for a certain number of years. And that number of years is what concludes your reliability. But in general, breaking the work for your team is highly important to make sure that you are actually making use of your resources. And of course, you have your reliability engineering and industrialization principles and your design for Six Sigma, design for assembly, and your design for manufacturing principles that you will have to take into account. So a well-rounded leadership at all different levels are very, very important. When I say all different levels, I mean all different levels of the V model as shown here. These are all different levels. Especially the leadership has to be extremely strong in these levels. The component development, ideation and development, verification, and the production side, it's very, very essential. I cannot stress that enough. Let's go here. For any high-level leader, the most important technical aspects to focus on when you're hiring or promoting or training your employees in terms of TEM Gen Z for now is optomechanics and precision mechanics. Now, this area focuses on engineering and design of devices that integrate both optical and mechanical components, emphasizing precision and accuracy in product development. Now, listen to this. Why am I talking about this? Why am I talking about hiring and promoting and training your employees? Because that's also something that your stakeholders and your shareholders and your investors will ask you constantly, again and again and again, in your board members. Trust me here. When you're sitting in one of these seats, this is not child's play. This is not, it's all foresight. It's not about sitting there and cutting costs. Yes, you do have to make certain hard choices at one point in your life when you're sitting in that chair, but at this level, at the level of being a board member of a startup or a scale up, it's all about what will you invest in. You need optomechanics and precision mechanics knowledge. You need the knowledge of customizing polymers, metal alloys, composites, optical coating, optical fibers. You need market influence. You need system, subsystem level knowledge. You need the understanding of strategic BOM development and optimization. BOM is bill of materials. It is all the different components that are there in the machines. At any point, strategically, you will have to make sure that you're not adding expensive of a component or too fragile of a component. Whenever things go wrong, the first thing that a mechanical architect generally looks at is the BOM, the bill of materials, to figure out where the problem could have come from. Strategic supplier selection and keeping the relations with those supplier, and of course the development of mirrors and lenses for photon and electron optics. It is not child's play. Communication, and then communication throughout all levels of the organization for multiple swim lanes of products and outcomes. These are all what you need to worry about when you're hiring the right people at various different levels of the organization. So, for instance, customization of polymers is not always necessary for a mechanical engineer, but it's necessary for a polymer scientist group, right? So things like that. I'm just giving a high level understanding of what you need to think of when you're developing a optomechanical startup from a product like Tangency. Of course, again, you need to worry about designing for vacuum, radiation prevention, and cleanliness. You have to worry about designing for cost, reliability, precision, manufacturability, assembly, and serviceability. Overall, it's nothing but design for excellence. Like I said in my introductory video, I am in environments where I am demanded of nothing less but then to be excellent in what I do. So yes, this holistic approach ensures that at every aspect of the product lifecycle, uh, um, high quality products are the end goal of the corporate strategy. So let's go back to our main page. We have discussed a lot this episode. We have talked so much about the product development, the architecture, how to organize your company, what kind of market analysis and insights you need, how to think when you're in a board level, what will be asked by your shareholders, your stakeholders, and how to make sure that you actually keep them pleased so that they can continue to roll out their wallets for you. It's quite a lot, isn't it? But this is the first episode. The second episode will go more into the details of the product itself. So please stick around. This was all about thinking how to build. This was all about thinking how to build a company around this product. Let's go and actually build the product now. See you in the next episode.